Hello folks, so we are going to look at chapter 15's homework, which involves problems 1, 5, 6, 7, and 9. So, starting with problem 1, given that Henry's law constant, or K sub H, oxygen in water at 25 degrees is 1.3 times 10 to the negative 8th moles per liter, pascals. Explain why the biological oxygen demand value of greater than 5 milligrams per liter is indicative of contaminated water. So we need to figure out, essentially, why is it bad when we have a biological oxygen demand of 5 milligrams per liter? So if it's greater than that. So we are going to convert the solubility of oxygen into the pressure of oxygen into the solubility of oxygen. So the solubility is equal to K sub H times its pressure. So that's what we're going to do. That's what we're going to do to start this one off. So hypothetically, at 25 degrees, the pressure of the air is 101,325 pascals. However, 25 degrees, vapor pressure accumulates about 3,200. So with that in mind, after you subtract out that, the pressure of the atmosphere is 98125 pascals. Now, with that in mind, oxygen is about 20%, close to 21% of the atmosphere. So the pressure of oxygen, with that in mind, is actually closer to 20557. We're going around to 0.2 pascals. So 20,000 pascals coming from oxygen. So with that in mind, the solubility of oxygen under standard atmospheric conditions, moles per liter times pascals times 2557.2 pascals would give us a molarity of oxygen of something like 2.67 times 10 to the negative 4th molar. Now, that means moles per liter. Converting that into milligrams per liter, times that by 1,000 to turn that into millimoles. That means that we have something like 0.267 millimoles per liter, and the molar mass of oxygen would be, in 1 millimole there would be 32 milligrams. Times 32 times 1,000. So the solubility of oxygen is something like 8.55 milligrams per liter. That is the maximum amount of dissolvable oxygen in water. So if the concentration of the biological oxygen demand is greater than 5, we barely have any oxygen left. So that's why that would be considered pretty contaminated. Okay. 5 is more of a thought question. Mineralization refers to the process by which organic forms of an element are broken down and converted into inorganic species. In environmental situations, this is most often a microbial process. For nitrogen, indicate what forms of element might be present in water or soil as reactants and products for the mineralization processes. So there's a lot of different options. But so consider, the hint I give you is consider all natural, biological, and anthropogenic sources of nitrogen, such as urea, proteins, humic material, NTA, herbicides. And also consider some of the species that can form either by cleavage or pronation, or by reduction processes. So, for example, urea, which is looks like this, can easily be converted into ammonia or ammonium. Various proteins can be converted. Proteins also have an amide groups. A protein has which can also be lost to ammonia. We also have uric acids. Uric acid can be generated to NO2 minus or even N2. And there's a lot of discussion about the nitrates and nitrites can be converted into nitrogen and dinitrogen monoxide in various microbial processes. So, I mean, this one's kind of just consider some of these. There's too many possible sources to really go into it too much in depth. But it's possible to produce nitrogen, NO2 minus, N2O, nitrates. It all depends on oxidizing or reductive conditions. Now, a better problem would be number 6. Using the thermochemical tables to calculate the PE standard values for the reductive half reactions involving nitrate in 3 different cases, where the product is ammonia, ammonium aqueous. So for 6, we want to calculate, try to flip this over. 6, we're going to calculate the PE for nitrate to ammonium, nitrate to N2O, and nitrate to N2. So we need a balanced equation for each of these guys. So we can figure out the number of electrons and what have you. But once we have the balanced equation, we can calculate the Gibbs value and then turn the Gibbs value into PE, because there is a direct relation of PE is equal to the Gibbs times 1,000 divided by 2.303 nRT. So, with that in mind. We can do that. And if we want to, then it says calculate the PE with normal water values for the same reactions, where we have to factor in the pH, a different pH, or the PE non-standard water is equal to the PE standard minus 1 over N log 1 over usually the H plus raised to the power of X. Okay, so with that in mind, nitrate to ammonia, we balancing this, one nitrogen, We need 3 waters here. That means 6 plus 4 is 10 hydrogens here. 9. And so that means we need 8 electrons. 8 electrons for this guy. 8 electrons. Okay. If I want to talk about and the way to potentially do that is let's see, and then for this guy N2O, I need to double that. So that means we have 6 oxygens. So we need, it's 5. We need 5 waters. That means we need 10 H's. So another 8 electrons. And this one, double that. 6 waters. And that means 12 protons. And that's going to take 11 electrons. Actually, no, my bad. This one's going to be, 10 electrons. 10. 2 plus cancels those 2 minus. So, looking up nitrate. The next step is to look up the Gibbs free energy of nitrate. Gibbs free energy of nitrate. And all the relative other things. You have to look up in tables. You can find these online. But it's a matter of finding a reliable table that has all your values. So NO3 minus has a Gibbs of negative 111.3. 111.3. H plus is a Gibbs of 0. We've artificially set it to 0. N2 has a Gibbs of 0. N2O is a Gibbs of 103.7. And ammonium has a Gibbs of negative 79.3. And water, in its many different forms, water aqueous, or not water aqueous, but water liquid, would be negative 237.1. 237.1. Okay. 237.1. So, products minus reactants. Negative 237.1 times 3 plus a negative 79.3 minus a negative 111.3 means we should have a Gibbs free energy of something like negative 679.3 kilojoules. So that is the delta G for the first reaction. Looking at the second reaction in the same way, negative 237.1 times 5 plus a positive 103.7. Plus a positive 103.7. Then minus a negative 111.3 doubled because there's 2 nitrates. And that would be negative 859.2 kilojoules. It all depends on your source of your numbers, but and my negative 237.1 times 6 plus 0 minus a negative 111.3 times 2. So that's negative 1200 kilojoules. So I have my delta G's. So with that in mind, to calculate my PE standard 1 of 1, it's going to be what? Negative 679.3 times 1,000 to get this into joules, divided by 2.303. There's 8 electrons, and there's R, and then there's 298. So, sounding, oh, and it's negative. So 679.3 times 1,000 divided by 2.303 divided by 8 divided by R divided by temperature. So PE of something like 14.88. 14.88 for the first one. Now, doing the second one. My PE2 is just the same process. Negative of a negative 859.2 times 1,000 divided by 2.303 times 8 times 8.314 times 298. So 859,200 divided by 2.303 and 8 and 8.314 and 298 gives us its even bigger reduction potential. And our third one. Negative of a negative 1,200 times 1,000 divided by 2.303, but now it's the 10 electrons, 314 and 298. Lastly, so we got 1200000, 2.303 divided by 10 divided by R divided by 298. So this is 21.03. So all of these have a very high PE under these conditions. However, that's assuming incredibly acidic. So with that in mind, we're going to modify all of these by a factor of 1 over n log of 1 over h plus raised to the power of the h's. And h plus is 10 to the negative 7th. So for the first one, for the PE of the water 1, we're going to say, so that's 14.88 minus 1 over 8 log of 1 over 10 to the negative 7th raised to the power of, there's 10 protons. So how does that change that? 10 root negative 7 raised to the power of 10. I'm going to invert that, do the log of that, and then divide by 8. So minus 8.75. So when all is said and done, 14.88 minus 8.75. In normal conditions, it's actually closer to 6.13. 6.13 is a slightly more reasonable number. Doing again, PeW2 is going to be 18.82 minus 1. There's still 8 electrons. There's still 1 over 10 to the 7th. It's still 10. So in this case, it's going to be minus the 8.75 again. 0.75. And so you get a PE of water of, in this case, 10.07. 10.07. So, too bad. And then the PE water 3, we got the 21.03. There's 10 electrons now and 12 protons. So 10 to the negative 7th, 12th power, invert that, logarithm of that, divide by 10. And so you got, this is actually 8.4. So it's actually a little bit less than you might, a little bit less of effect than the other ones. So this is PE of 12.63. So that's our actual reduction potential at those values. So let's repeat, since this was a heavy math one. Step 1, I balanced the chemical equations with the number of electrons and number of protons and the number of waters. Step 2, I looked up my delta G values and found my delta G reaction for the following reactions. Step 3, using the delta G to PE equation, right here, I converted delta G value to the PE very easily. And number 4, I modified this with the amount of, based on the number of acids, to get the PE of water using this equation there. I modified my PE to the PE of water by changing the pH, which allows us to calculate a much more accurate value. Now, not all of them are heavy math, so we'll just keep going. The last 2 are not math. Evolution of ammonia is one process that can result in the transfer of nitrogen from aqueous systems to the atmosphere. Discuss environmental conditions that would favor such process. Would you expect ammonia evolution to be significant in an acid bog or in the oceans? So, consider how ammonium is produced. Consider what conditions would needed to convert ammonium to ammonia. Would either of these situations contain both of these? So for nitrate to be converted into ammonium, you need, remember there's the electrons over here. So this is a reducing conditions to get to here. For ammonium to go from aqueous to a gaseous state, we need a base. So we need, for this to work, we need ideally both reducing and alkaline conditions. Reducing and alkaline conditions. Now, in an acidic bog, there is reducing conditions. There would be anaerobic conditions that could consume this and convert it to ammonium. In the deep ocean, yes, there is also anaerobic conditions that could reduce nitrate to ammonium. But under the acid bog, by the very name of acid, it's going to keep the ammonium as ammonium. We need alkaline conditions to convert this to ammonia. So the ocean is likely to produce more ammonia than acid bogs, more gaseous ammonia. It will typically have a higher pH in the slightly basic range, and the wave action, in fact, can help stir this out and help the ammonia escape. So there's going to be far more ammonia in the ocean. But so this one's just ocean and the bog. So the ninth and last problem. Why are reduced gaseous species of sulfur emitted from rice paddy fields, swamps, and the near shore borders of lakes, but not from open lakes? So, even though reduced sulfur compounds are found in the sediments in all of these situations. So basically we have some HS minus. Well, we have some. We have to think about our sulfur cycle and how these get produced. So why are gaseous sulfurs? We need to produce these and convert this to H2S. So we need acid to do this, but we were saying sulfates to go to HS. So this reduction process needs essentially anaerobic conditions to form this HS. Under aerobic conditions, it can be oxidized back. So we need to keep some anaerobic conditions throughout. So rice paddy fields, that's really easy to understand. It stays anaerobic so long as it's flooded. Same thing, swamps. You get a lot of sulfates and it's converted to hydrogen sulfide. And these are typically produce acids as a byproduct. So these are places where the oxygen content is low. The shore borders near the lake, while they're not, you wouldn't call it deep ocean, we're talking in the shore borders, we're talking in the sediments of the lake. So they contain some organics. It's organic rich, just like rice paddies and swamps. The key there is we need organic rich anaerobic conditions, not just anaerobic conditions. We need lots of organic material for this to work. The lake shores, the sediments will have organic, but the open lake, in the middle of the lake, there's not a whole lot of organic material. Even though the oxygen content may be low, there's not the organic material that's needed to consume this and convert this. So any sulfides formed in the middle of the lake might be, in fact, precipitated as various salts. But once they get deep enough, it's even possible that maybe the sulfide would be resolubilized. But the idea here is we need organic matter as well. We need that plus sulfate to go to our HS. And because we don't have usually both of that in the open lake, we don't see the same degree of reduction. But, okay, that is what we have for Chapter 15. I bid you adieu.